Okay. Hello, Shahjahan sir. Can I start?
No, sir. I will be introducing you to all the participants. So just give me a minute.
Okay.
Yeah.
Okay. Fine. Okay.
Good morning, dear participants. Today we have with us a distinguished speaker, Dr. S.S. Krishna Chaitanya. Dr. Krishna Chaitanya was born in 1984 and he received his BTech degree in Electronics and Communication Engineering from Pondicherry Engineering College. He was also the recipient of the Thales French Ministry of External Affairs Scholarship in 2007. And subsequently, he received his MS degree from Telecom Paris Tech in France in the year 2009. From 2010 to 2011, he was a project officer with IIT Madras, and 2011 to 12 he worked as an electronics engineer at the Institute of Electronics, Microelectronics and Nanotechnology at Villeneuve, France. He obtained his PhD degree in radio communications from CNAM Paris, France in 2016. And 2016 and 17, he was postdoctorate at the National Institute of Applied Sciences, Rennes in France. Since 2018, he has been affiliated to the Mahindra Ecole Central, Hyderabad, as an assistant professor. His research interests include digital signal processing, digital communications, embedded systems, so a pretty versatile range of specialization, and also with focus on deep learning, massive MIMO, HPA linearization, PAPR reduction. So I guess sir will talk about it today, and channel estimation as well as receiver synchronization techniques. So it's a broad spectrum of topics, and he has also authored several international and international conferences, journal, and also holds an European patent. And further, you can see that he has been involved in quite a few European and French research projects involving broadcasting systems and PMR systems. So Dr. Krishna Chaitanya, I welcome you. And at the outset, let me thank you for being with us. And we can begin now. Today, we will be talking about 5G waveform design. And I will now stop sharing my screen, and sir, you can proceed after that.
Okay. First of all, thank you very much for giving me a very good opportunity. So the lecture will be on the 5G waveform design. So I thank you everyone for giving me this opportunity. So first, before going for this waveform design, we will try to understand what waveform is. Okay. So let's get introduced to what waveform is. It all started with Claude Shannon. He has given a geometrical representation of communication systems way back in the 1950s. So according to this kind of representation, so messages and the corresponding signals are nothing but points in two function spaces. They are message space and the signal space. And at the transmitter, each message is mapped to a particular signal in signal space, and the receiver does the demapping. Okay, so as long as this mapping is 1-to-1 from message space to the signal space, that is, it is injective mapping, a message can always be recoverable at the receiver. So what is a waveform? A waveform is nothing but the physical shape of the signal that carries the modulated information through a channel. It means that it corresponds to a specific structure in the signal space and identifies the formation of the signals. When this particular structure release on multiple simultaneously transmitted subcarriers, it corresponds to a multi-carrier scheme. I think that you all are well versed with what is a multi-carrier modulation scheme is. I'm not going into what is a need of going for this one. Okay, but just I wanted to give you the mathematical understanding of what a MC scheme is. So any multi-carrier scheme, I can mathematically represent it in this particular way. Here you see that here the DMN, it is the message which is being transmitted in the form of symbols. Okay, over n subcarriers, capital N subcarriers, and this particular function. This function, we call it as synthesis function, because our original information is in the frequency domain, and this synthesis function will bring it back to the time domain. Okay, so this function, what it does is that it maps the symbol in the message space to the signal space. Okay, and the small m, it is the time index. This function Gmn of t, the family of this function, we call it as a Gabor system. How I can get the family of these signals is that first I take one single prototype function. Okay, and this function I can translate it in the time domain, which you can see. So I am translating it with respect to the symbol spacing, and I can also rotate it in the time domain. Means I can translate its spectrum in the spectral domain. So that the translation space in the spectral domain, it will be the subcarrier spacing. Okay, so all the possible translations and rotations of this one. So means for all the values of m and n. So what and all functions I can generate, this whole bunch of functions, I call them as a Gabor system. This starting function means the initial function from which I'm making all these operations, we call it as a Gabor atom or prototype filter. Okay, many people working on the 5G systems, you'll be hearing this word called prototype filter. Okay. So this understanding is important to have some in-depth analysis about what kind of multi-carrier scheme we need for any generation, whether it is 4G or 5G. Okay. So what are the fundamental elements of a waveform? So first, before going for that, if I am transmitting a signal S of t from the transmitter to the channel, so what it comprises of? So first question we need to ask is what to transmit. You are transmitting message in terms of symbols. Okay, so one element is symbol, and second is how I am transmitting it. Okay, so for that we will be filtering them. So filtering in the frequency domain is nothing but shaping, because it's a convolution operation. So we use a pulse shaping filter to filter out some unwanted frequencies before the transmission. Okay, and then where to transmit it. So on a two-dimensional frame of a time and a frequency, we'll be placing these filters. Okay, these filtered symbols will be placing them, okay, before transmitting them. So in terms of time, so I can do that by translating it, and placement in the spectral domain will happen where I am, in which subcarrier spacing I am using and all. Okay, so these are the three questions we have to keep it in our mind when understanding what a waveform is. Okay, okay, and then why we need new waveform in 5G? We already have some waveform in 4G, but what is so special about 5G? So the design criteria of a new waveform, it depends upon the demands of users, channel conditions, what particular system I'm working upon, and also the technology criteria. Okay, and this design criteria change with respect to the advancement of technologies. Okay, so the waveform techniques which are previously used from 2G to 4G, they may or may not meet the demands of the next generation wireless networks. This we have to keep it in mind. Okay. So how a particular waveform is so suitable to a particular technology, we try to understand it in terms of some key performance indicators, which we refer as KPIs. You will be often hearing this word called KPI. So these KPIs, it can be peak data rate, or the user experience data rate. I mean the mean data rate, spectrum efficiency, how much mobility it can support, how much latency it can have, and how much users it can support, how efficiently it is able to utilize the available energy, etc. Okay, so and you can see the comparison. For example, if I want to see in terms of the spectrum efficiency, we know that the spectrum is a very costly entity. Okay, we cannot use it in whichever way we want. We have to use it in a very judicious way. And in the 5G, we are aiming to increase the spectrum efficiency in a threefold way. And also the peak data rate, we wanted to increase it by a factor of 20. And also support high mobility as well, with low latency, and supporting more number of users. Okay, so keeping this in mind, keeping this a high expectation in mind, and what are the possible application areas which we can have. So 5G application areas have been broadly classified into three key application areas. Previously, it was all about communication. So 2G, 3G, 4G, it is all about just about voice and some video communication, voice communication. It is just that. But in 5G, it is not just that. It is not just real users who will be utilizing this technology. It can be many things as well. So we are talking about the concept of Internet of Things. It can be anything which can connect to the network. So if we see the different application areas, one area is about the smart city. So which we are hearing nowadays in India, smart city. Of course, my city, Pondicherry, is also considered to be a smart city. So a smart city means to have good video surveillance. So it can be surveillance, or offering Wi-Fi, very good Wi-Fi connectivity, or maybe good guidance to avoid traffic jams. It can be anything, ranging from any of these applications, and these are, they are not users, okay, they are things, they are some systems which are involved in that. And then you can have some mission critical applications, for example, some surgeries happening where the patient is in India but the doctors, they are located in Europe. So you need to have a reliable communication link, and at the same time the communication should have a very low latency. And also it can be like a self-driving car, and we have another application like augmented reality. And also some people, they want a very high speed. Okay, so keeping all these applications in mind, the 5G application areas, they are broadly classified into three aspects. One is MMTC, so massive machine type communications, and another one is ultra reliable low latency communications, and enhanced mobile broadband. Okay, so in this one, it's more emphasis will be on the speed. For the MMTC, it will be not the real users, but a lot of machines will be interacting with them each other. And in this, the third one, the communication should be ultra reliable, and the latency should be very low. Okay, so keeping that in mind, for these key application areas, we know that we cannot offer everything. Okay, because there is a lot of trade-off involved. So we try to give priorities for which KPI I have to give high importance, which I have to give medium and low importance. For example, when I wanted to talk about the MMTC, so the main emphasis will be on the connection density, because they will be deployed at a massive scale. Suppose I wanted to, for example, in France, at every bus stop we have a Wi-Fi hotspot. Imagine in a city like Hyderabad or Chennai, how many bus stops will be there? Bus stations, railway stops, airports. And it's just not that. We can have like traffic surveillance, many things. So the number of connected users, it may not be the real user, it can be systems also. So that has to be taken in mind. So that is high importance. Okay, but at the same time, because they are massive in number, the network efficiency, how much energy I am utilizing for them, that also have to keep it in mind, but that is of medium importance. And if I go for the URLLC, the main emphasis is on the latency, means I want to, the emphasis, high importance on latency means I want it to have very low latency and also support high mobility. And for the enhanced broadband, you can think of it like an upgradation from 4G to 5G, just in terms of speeds, spectrum efficiency, and on. Where the latency and connection density, they are not of much high importance. Okay. So, what is the state of what RAT we have? RAT means radio access technology. So in the 2G, it is dependent upon FDMA and TDMA. For 3G, we know that it is depending on CDMA. 4G LTE is based on OFDM. For 5G, we can notice that it has very high ambitious performance goals in terms of traffic, latency, battery life, data rate, etc. Okay, so keeping all this in mind, we also need to take into consideration that the 5G communication systems, they have heterogeneous network structure, which was not faced before up to 4G. Means that apart from people, many things, they can be also using this network. Okay, it can be your camera, it can be some temperature, some sensor, anything it can be, or some remote sensor in some fields. So just to sensor how healthy my crop is, it can be anything, or some defense surveillance to check the intruders near some international border. It can be anything. Okay, so this we have to keep it in mind, that it has heterogeneous network structure. And another aspect is that each user has different features in his mind, whether it is a packet length, the data rates, transmission frequencies, capacities, and with each user their needs will vary. For one user it is data rate, for another user it is the capacity. Okay, and apart from that, since there are also things involved, you have a lot of user asynchronism. Asynchronism can lead to synchronization issues in time and frequency domains. This is going to be a very serious issue for OFDM. The OFDM which we are using in OFDM, it is very sensitive to synchronization errors. So to overcome all these problems, we need to design some new multi-carrier technique which can use spectrum in efficient way, offer high data rate, consume low energy, and have low latency. Okay, and why we are talking about waveform design now? First, let me build the whole 5G framework, and then okay, parallelly we can have this waveform design. But that is not the case, because if you see here the 5G PHY and the MAC layer, so in the entire 5G energy framework, the waveform design is the choice of which waveform I want to use. It is occurring initially after the spectrum. So it is something like a foundational block. Only when the foundation for a building has been laid, then in future I can think of like, okay, how many floors I want, what interior design I want to have, all that. Once this waveform is fixed, then I can think about like, okay, what should my frame structure should be, what kind of modulations I have to use, and duplex mode also, whether I have to go for full duplex, FDD, TDD, all that. So first, it is important first to finalize on the waveform, which particular waveform I have to use. So this gives that how much important it is to finalize on the waveform design. And what is wrong with OFDM? Can't I do with OFDM simply by increasing the CP length? I can try to go for very good synchronization techniques. Can't we go for that? So this question was already there, because OFDM is currently the dominant technology in broadband communications, be it Wi-Fi, WiMAX, 4G LTE, even broadcasting TV also, the TV broadcast also. But it is having some basic limitations. The limitations are that it requires cyclic prefix. So cyclic prefix means it decreases the spectral efficiency. And as I mentioned earlier, it is highly sensitive to the synchronization error, means in terms of the frequency and timing of set, because it leads to the loss of orthogonality. If orthogonality is gone, why we are talking about orthogonal frequency division multiplexing? Okay, so at any cost we have to maintain this orthogonality. This was the issue. But for the 5G, we are talking about carrier frequencies at millimeter wave range. Okay, for those frequencies, even phase offset is also coming into the picture. It can severely impact the performance of OFDM. Okay, and thirdly, last but not least, OFDM has a high PAPR. Okay, for the first two, I can try to do some or other thing to compensate that. But because of its high PAPR, it is having direct impact on power consumption. Today, everybody talking about save power or consume less power, try to try to make sure that you are not wasting the power consumption, having more power consumption. And apart from that, more power consumption means that we are also involving in more carbon emission as well. I'm talking in terms of the ICT, okay, information and communication technology industry. So this is a very serious issue. So because of this point, people started seriously thinking about alternative waveforms way back during the 4G time. Okay, what happens if a PAPR is high? If the PAPR is high, the RF impairments, which are already there in the modern communication system in terms of the power amplifier non-linearities, it can have severe severe impact in terms of the in-band and out-of-band distortion. The in-band distortion means it will degrade my bit rate at the receiver by altering, by distorting my my constellation, my signal constellation. And out-of-band means that whatever spectrum I am having, so because of the nonlinear power amplifier, there will be spectral regrowth will be there. Already for the OFDM, in the spectrum is a sync function. Sync function means the side lobes are already high, and on the top there will be spectral regrowth will be there. So I have to maintain some gap before I can accommodate another user. If you have noticed in LT, suppose my bandwidth is around 10 megahertz. So 10 megahertz means total available subcarriers are 1024 subcarriers. But in that I am using only 600 subcarriers. The remaining one, this is what I am doing. I'm wasting those subcarriers just to keep some space so that I can accommodate another user. Okay. So this is a big issue. We know that the spectrum is a very costly commodity. Okay. So this high PAPR problem, is it just with the OFDM? No, it is not. Every multi-carrier scheme, it will have high PAPR. It is coming from the central limit theorem. Means when your FFT size is increasing, more severe this high PAPR problem will be. But we all know the need for a multi-carrier scheme in modern day communications. Okay. And this high PAPR, it poses very serious challenge to the design of power amplifier. And the power amplifier, it is one of the costliest component in a communication system. And also it consumes a lot of power. Okay. So the power consumption is having a direct impact on the battery life. Every time I cannot change the battery now and then. Okay, so because of this, when they were talking about mobile wireless communications, in order to have a mobility in the uplink, when you saw the mobile handset which we have, we cannot keep on charging it for every 15-20 minutes. So taking that into the account, instead of OFDM, single carrier FDMA has been proposed as a immediate remedy. Okay, but since then, because of this high PAPR issue, people started to seriously study for some other waveforms for the 5G, and these waveforms are referred as post-OFDM waveforms. Okay, so as we know, what are the fundamental elements of a waveform? They are symbol, pulse shape, and lattice. Okay, so in that symbol constitute the random part, and the remaining two, they constitute the deterministic part of a waveform. So symbols. A symbol is nothing but symbols, they are nothing but a set of complex numbers in message space that is generated by grouping the number of bits together. Okay, so how many bits I am grouping, I am mapping to one symbol, it impacts the throughput. Okay. The transmitted symbols, they can be either complex or real. This mapping will be complex only, it will map to a complex number. But I can do one thing, a complex number I can split into two parts, the real part and the imaginary part. They both are real numbers. So instead of a complex symbol, I can transmit the real part and the imaginary part. So it means that I am transmitting real symbols. Okay. And the pulse shape filters. So a pulse shape, it is a form of the symbol in the signal plane, which is defined by the characteristics of that particular pulse shape filter. Means that the shape of these filters determine how the symbol and energy is spread over the time and the spectral domains. Okay, so if a signal is more spread in one domain, then it is more localized in the other domain, which we know from the properties of Fourier transform. Okay, so this has how much it is spread in one particular domain. It has an important effect on the signal characteristics. Okay, so how I can classify these pulse shaping filters? First classification it is done in terms of matched filters. First we check if it is a matched filter or not. Matched filter means that at both at the transmitter and at the receiver we are using same filter. Okay, so if we are using different filters, then it can, we say that they are unmatched filters. You know that matched filter means that they can have maximum SNR in a AWGN channel. Okay. And the second classification, it is in terms of the orthogonality. So if G and H are the filters both in the transmitter and the receiver, you all know the orthogonality condition. I have to take the inner product and I have to check. Okay, so if they satisfy the orthogonality condition, they can be either orthogonal or bi-orthogonal. If they don't satisfy, they are non-orthogonal schemes. Pure orthogonal means both these filters are same. I'm using the same filters. In bi-orthogonal means both are different filters, but still they respect the orthogonality condition. Why we want to go for bi-orthogonal schemes? Because they can offer better performance in dispersive channels. Okay. And the last classification of pulse shape filters is in terms of localization. Okay, so localization in terms of the time and the frequency plane. Okay, so the localization in time, it is measured by the square of the norm of t into p of t, where p of t is the filter. Similarly, the localization is frequency is measured in terms of the frequency into the spectrum, where the capital P of f is the Fourier transform. Okay, so when I take the product of these two, if they tend to infinity, then it is a non-localized filter. Else they are localized filters. Okay, and lattice. So lattice, it is an abstract concept. Okay, it corresponds to an algebraic set generated by sampling the time frequency plane. So the location of the samples, they define the coordinates of the filters in the time frequency grid. Okay, so at these locations, the modulated pulses are placed in the two-dimensional plane. Okay, and I said it is a two-dimensional plane. So I can also add one more dimension to it thanks to the MIMO technology. So I can add the third dimension, which is a space domain. Okay. So a lattice, it can be described as a mathematically as a non-unit generator matrix. Okay. So in this generator matrix, we can see that here x and z, they are not supposed to be equal to 0. So by the way, how we define it, that tells us what the geometry of my lattice is. Okay, so this geometry, it identifies the distance between the points. So we have different type of geometries. Either we can have a rectangular lattice, hexagonal one, or another one also. The more popular ones are the rectangular and the hexagonal ones. And another salient aspect of a lattice is its density. So how I define it? The density of a lattice is the reciprocal of the volume of that lattice. The volume is nothing but the modulus of the determinant of this matrix. Okay, so then this lattice density, I can say that it is either undersampled, critically sampled, or oversampled. And then comes a very important theorem. Okay, it is the Balian law theorem, which states that there is no well localized function in both time and frequency for a Gabor basis of unit lattice density. The best example is if you have a rectangular function in the time domain. Its spectrum is a sinc function. So rectangular is very well localized in time, but it means that the spectrum it spans till infinity. Okay, if this constraint we were not having, then waveform design would have been a very small task. But we are living in a real world where we have all these constraints, so we need to take that into account. Okay, so keeping this issue, what was done, instead of a rectangular pulse, Salzburg, he has suggested way back in 1960s that why can't we go for a hexagonal pattern where I stagger it. Somebody who may be working on post-Waveform waveforms, you may be hearing this word called time staggering and staggering it, or OQAM, okay, offset QAM. This lattice staggering, it is also referred as offset QAM. So what I do, instead of the complex symbol, I split into two real parts, means the real part and the imaginary part. So both are two real symbols, okay. So then I will be placing them. You see here the filled circle represents the location of the filters on the cosine plane, and the empty ones represent the location of the filters in the sine plane. If you notice, if you compare both, you see that for the first symbol I am trying, so initially I am trying to fill in the location 1 and 3, but subsequently I will be filling at 2 and 4. Okay, also in the same here, when I am filling the real parts, first time I am filling 1 and 2, but the next subsequent I am filling 2 and 4. So this staggering, okay, so he has proved that if I can maintain this, the time spacing and the subcarrier spacing, if they follow this condition, then I can maintain the orthogonality. Since I am placing the real symbols, the orthogonality which we achieve here, we call it as the orthogonality in the real domain. In a rectangular lattice where we will be placing the complex symbols, the orthogonality will be in the complex domain. Okay. So to summarize that, we can see that the multi-carrier schemes in terms of filters, lattice, and the symbols. So what are the all possibilities we have? And then we see that since orthogonal filters means I'm using same filters both at the transmitter and the receiver, it means they are matched. Okay. So another thing is the important one we need to take is the lattice density. Okay. So based on the lattice, which lattice I'm taking, whether I'm doing staggering or not, so that will also impact what. So I'm achieving orthogonality in which domain. So real domain means I'll be using only the real symbols. Complex domain means I'll be using the complex symbols. So it means also symbols, I can have my transmitted symbols. They can be finite in number, infinitely large in number. Okay. So what are the existing schemes, multi-carrier schemes, or the proposed ones? Okay, the proposed schemes in terms of the orthogonality. Okay, so the orthogonal multi-carrier schemes, the easiest one is a zero-padded OFDM. What we do for the OFDM, so in order to combat the effects of a multipath channel, I will be padding it with zeros. Okay. This is popularly known as God-interval. Okay, by doing this, I am changing the lattice density. Okay, and we know that the filter which is used in the OFDM, it is a rectangular filter. Okay, so rectangular filter means the frequency domain, the spectrum, it will be shaped in form of a sinc function. Okay, and then we have filtered multitone. The filtered multitone, the filters, they don't overlap in the frequency domain, and the guard bands between the subcarriers can be utilized in order to achieve filter localization in the frequency domain. And no particular filter is associated with that one. We are free to go for whichever filter we want. So here we wanted to avoid the overlapping in the time domain. Here we do the same, we aim at the same in the frequency domain. And there is one more scheme called lattice OFDM. It is the optimum orthogonal scheme in time so it is aimed for the time and frequency dispersive channels with an objective of minimizing the interference between the symbols in the lattice, and also it depends upon different lattice geometries and orthogonalized Gaussian pulses. And then we have orthogonal MC schemes with a lattice staggering, means here the orthogonality is in the real domain. And the popular ones, they are staggered multitone, also known as filter bank multi-carrier, okay, and a cosine multitone. So they are both same structurally, but the only difference comes in which type of modulation I am using. The FBMC or staggered multitone, it uses QAM, okay. Whereas the CMT, it is dedicated to the vestigial sideband modulation. And from one scheme, I can synthesize another one simply by applying some frequency shift operation and proper symbol placement. Okay. And then we have the Bio-Orthogonal MC schemes. The one which we are using in 4G, the dominant scheme, which is prevailing till date, it is the CP OFDM. When we talk about OFDM, this is what we are talking about. Okay, so here the plain OFDM, instead of simply zero padding, what I try to do, I try to introduce a cyclic prefix. So I copy some part of the symbol at the end. So by doing this, again, I am stretching the lattice in the time domain. So because of this stretching, at the transmitter, I'm supposed to have a longer rectangular filter compared to the receiver. It means that we are having unmatched filter. But what is the advantage of CPOFDM? Because of the complex domain orthogonality, we can go for the single tap equalization, and since they don't overlap, the symbols don't overlap with each other. And also we have the simple synchronization. Okay, and then we have filtered OFDM. So the same way of OFDM, in order to remove the high side bands, what we can do, we can simply filter it out with a good filter. So if the windowing is performed with an additional guard band, such that the density is greater than 1, then we can have an Bio-Orthogonal scheme. Okay. So this is what when people talk about windowing or filtered OFDM. And then we have Bio-Orthogonal Fdm. So this is being proposed because the CP-OFDM, it don't treat time and frequency dispersions equally under double dispersive channels. Okay, so in order to deal with this issue, this BFDM has been proposed. And then you have non-orthogonal schemes such as generalized FDM or GFDM. So where the correlation between the points in the lattice is allowed in order to utilize well localized filters with the unit lattice density. Okay, it utilizes complex symbols and also requires cyclic prefix with the tail biting. Okay, at the receiver side, successive interference cancellation is deployed to remove the ISI. And we have a few more non-orthogonal schemes based on faster than Nyquist, the partial response signaling, etc. Okay. Apart from that, there are some multi-carrier schemes with the spreading approaches as well. The spreading is done mainly with an intention to deal with this high PAPR issue. Okay, so what we actually do, the modulation symbols are mapped to multiple points in the lattice. So we can think of it like I'm introducing another Gabor system. Okay, so another Gabor system that spreads the energy of the modulation symbol into multiple subcarriers. Okay, so we'll be having two Gabor systems. So the second one, so it is involved in the serial to parallel conversions. Okay, and parallel to serial conversions at the means on one side I will be having serial to parallel, and another side I will be having parallel to serial conversion. Okay. So the popular one which we have seen in 4G, it is the SCFDMA. It is also referred as DFT spread OFDM. Okay. So if I am talking in terms of real domain orthogonality, so I am talking about staggered multitone. So there also I can do the same spreading. So there we refer to that kind of scheme as FB that filter bank spread FBMC. Okay. For the 5G NR uplink, without changing the waveform, we are pi by 2 BPSK is suggested to reduce the PAPR. Okay. So a brief overview. So till date in the 4G we have in the downlink we have the OFDM, uplink we have the SCFDMA. Okay. And then we have another class of the 5G waveforms based on FBMC. Okay. So we try to see the overview in terms of the complexity. For the OFDM and the SCFDMA, the complexity is less and it releases only on one tap equalization. Whereas for the FBMC, it is high because we are having synthesis filter at the transmitter and analysis filter at the receiver. Also, the equalization, it is not one tap because the symbols overlap with each other. And one advantage with the FBMC is that it don't require cyclic prefix mean. Okay, whereas the previous two, they require cyclic prefix. This frequency is synchronization. When we talk about synchronization, if there is user asynchronism, means when there are asynchronous users are there, then we will be having a poor frequency localization. Okay, this issue is not there in FBMC in the presence of an ideal power amplifier. The time localization, it is good due to the presence of CP. Since there is no CP in FBMC, it is poor. For the support for MIMO, it is straightforward in the former two because of the single tap equalization and also the complex domain orthogonality. For FBMC, it is not as straightforward. This is a serious drawback for FBMC based waveforms. Okay, this is a big constraint. And the robustness to CFO, it is poor in OFDM, a little bit better in terms of in SCFDMA. In the case of FBMC, it is very good because of the employment of different ad hoc prototype filters. Okay, the support for frequency selective link adaptation. It is supported given there is some inner frequency granularity. Since in SCFDMA it is a single carrier one, it is not supported. For FBMC also it is same. And I have not covered all the proposed waveforms. Many waveforms are being proposed, but some key design features we have to keep it in mind. First thing is the complexity, where the complexity is in the the first thing we need to take into account is the orthogonality. The orthogonality, whether it is in the complex domain or in the real domain. Okay, so in the complex domain, we will be seeing all the CPOFDM. You have filtered OFDM, filtered multitone, FFDM, FBMC. You may be hearing also about the OLA OFDM. Okay, for the FBMC OQAM, it is the complexity is in the real domain, and we have some non-orthogonal schemes such as GFDM, and then filtering. For CPOFDM, it is not required, so there is no filtering at all. Suppose if I talk about FBMC OQAM, yes, we need filtering both at the transmitter and the receiver. And the granularity means I am filtering each subcarrier. So subcarrier level filtering is done. Filtering means it is a convolution operation. So the convolution, it is a linear convolution. Okay. So we can see, and in FBMC OQAM, the guard interval, it is not required. So likewise, we can see that for different waveforms, we can see if guard interval is required, or if the filtering is required, then what is the granularity if I am filtering. So there is something called block filtered OFDM, where we filter a bunch of subcarriers. Okay, so at resource block level, and the filtering is not required at the receiver. Okay, yeah. So some of the references which I have sought are one very good article by Yahya. He is from the Cedric team in France. So they were one of the group who has proposed the FBMC waveform. They're part of the FDIA's team. So I am also from that particular team. And another one, another article which I found very interesting was this survey paper, which was published way back in 2013. Okay. So you guys, if you have any questions, you can ask me.
Yeah, so thank you, sir. Participants can please post their queries either in the chat box, or you can unmute your mic and ask questions to sir.
Yes.
Sir, there was one question in one of the previous sessions that was to do with the relevance of pi/2 BPSK.
Yes.
So I saw that in slide number 41, you made a mention of that in the context of PAPR, if I'm not mistaken. So could you please, if you don't mind, explain what is PAPR, why is it so important, and the relevance of pi/2 BPSK, please, sir.
Okay, so this PAPR means that, okay, in multi-carrier schemes, we will be having a lot of subcarriers. So I am having an FF50, an IF50 block in the transmitter side. So because of this IF50 operation, we see that many random peaks, they can occur for the time domain signal. And another thing is that as the FFT size increases, so more number of subcarriers, they will be contributing to the peaks. First, the occurrence of peaks, they are random in nature. If the FFT size increases, they will be more recurrent. Okay, they are random. They will be more recurrent if the FFT size increases. And second thing is, sometimes these peaks, they can be very, very high. Okay, so because of this, there will be a problem in designing the dynamic range of the power amplifier. In a simple sense, everybody in our household, they're more worried about the power fluctuations when they're having big loads, such as washing machines, TV, some heavy loads. When they're having the huge fluctuations in the power supply happens, they're more worried about that. Likewise, here also, when there are huge fluctuations because of the power amplifier, it is a nonlinear component because of it is built from transistors. So it will be distorting the constellation. Not only it distorts the constellation, but also it creates artifacts of my spectrum so which we see it in terms of a spectral regrowth. Okay, so this is a very serious issue which was first observed in 4G, both in terms of the power consumption or also how many users we can accommodate. Okay, and because of this, since we are using OFDM, there is no other choice for us where we have to keep a lot of spectral gaps, which we call as spectral holes. Okay. And because of this, suppose in the public protection and disaster relief in Europe, they are using PMR systems. They are not able to provide the broadband services just because of the issue of the PAPR in the OFDM. Okay, there are many techniques to deal with this, whether we can go for the PAPR reduction techniques. There are also some techniques based on linearization of the power amplifier. So what they are doing in the 5G, in the uplink, as of now, So without changing the waveform in the plane, just they're changing the modulation. Okay, so when there are more concentration points you have, so if the each concentration point when I'm using, if the concentration size, the size of the concentration increases, then it can also have some impact on the PAPR. So for that, what they proposed is that if I use the pi by 2 BPSK, so what I will do between symbol to symbol, there will be a pi by 2 phase shift will be there. So if you just see the constellation, it looks as if that it is a QPSK constellation, but in reality it's just BPSK. Okay, so without changing the waveform, just I am choosing a good simple the mapping scheme, that's the modulation scheme, just to reduce the PAPR. Actually, in this lecture, I have not concentrated upon the PAPR and the predistortion. Next month, I am having one more online lecture for on this something, this AICT, this ATAL. This platform. So it is upon the energy efficient techniques in 5G. My specialization, it is on this PAPR reduction techniques and the predistortion techniques for the 5G and the next generation communication systems. Maybe if somebody is interested to have more in-depth understanding, they can attend that lecture also. In this lecture, my idea was to help the students who are doing PhD or some research on 5G, post 5G waveforms, to understand what a waveform is, what waveform design is, what are the things I have to take it into the consideration, what is so-called real domain orthogonality, what is this lattice geometry. So just I want them to have some basic understanding about that. Okay.
Yes, sir. Yes, sir. Thank you. And we'll take a couple of questions if you have 5 minutes more, sir. Is that okay?
Yes, sure. Of
okay,
course.
okay.
Of course, sure.
So, sir, I think two questions. I think they intended the same. I mean, both mean the same thing. So, one is that which 5G waveform is most suitable and in use, and the other one is that out of the proposed waveforms of 5G, which waveform is the most preferable one. So a similar question, so a common answer, sir.
Sir, till now there is no consensus. So because there is no consensus, as of now we are stuck with OFDM. So in the 5G, so for the carrier frequency, they are in two phases. The first phase is that the carrier frequency will be less than 28 gigahertz. The second one will be greater than that. They were aiming to go as high as 60 gigahertz carrier frequency, means millimeter wave. For the second phase, definitely it will not be OFDM. For the consensus, whether we have to go for OFDM based ones, means the rectangular geometry lattice, or the FBMC based, still there is a lot of discussion going on. And then we have some political pressures as well from countries like China to push some particular waveforms. But as of now, there is no consensus. For example, yes, somebody is trying to ask. Yes?
No, sir, that was me. Please continue, sir.
Yeah, for example, in the public protection and disaster relief, so they are. It is based on OFDM. So this means this we use for when there is some earthquake or some floods are happening. So how efficiently the government can help the people to come out of this disaster. Okay, so for that we have everything else. We have the spectrum, we have the technology, everything else we have. But because of this high PAPR issue in the OFDM, we are not able to offer the broadband services. Okay, broadband services, maybe you can think of it like video. Instead of just having some voice communication, you can even also have some video communication. So for that, we have worked in some European project where we have proposed that FBMC is a very good alternative. But as of now, which we see, what we understand till now is that there is nothing called best. If I want to have something frequency localization, then I have to compromise in the time domain where there will be overlapping between the symbols. It means that I cannot have very easy equalization. If easy equalization it is not guaranteed, then it will have the impact when I'm using multiple antennas. So there are a lot of trade-offs involved. Okay, so we have to sacrifice some in order to achieve some. That's why in 5G, instead of having one particular application area, key application area, it is divided into three different areas. Okay, so as of now, there is no consensus. In Europe, lot of teams, they are working on FBMC based waveforms. Okay, for example, my team in the Cedric lab in France, which I am also an associate member. So they are also working on the waveform design. They are now concentrating on FBMC and also block filtered OFDM.
Yeah, thank you, sir. One more related question. I mean, before that, I think I'll take a question from Madam Deepa. So the question is, how do we analyze the performance of 5G waveform-based systems in real time?
See how we analyze. There can be different parameters. So one parameter is to see. Okay, I'm talking only in the physical layer level. Okay, so in the physical layer level, I can think of it like at the quality of the transmitted signal. We can analyze in terms of the modulation error ratio. So this metric is proposed by ETSI for broadcasting systems. But it's a very interesting metric. It will tell about how good my waveform is even before I am sending it to the channel. Okay, so after taking the RF nonlinearities into the account, so this MER will tell. This MER is closely linked to the EVM. Okay, so the quality of the signal at the transmitter, we can think of it like MER, and at the receiver we can go for, obviously it is the bit error rate. Yeah, so these are the two in, I'm talking only in the physical layer.
Yeah, that is true. So that is correct. So just one last question, sir. In the Indian context, which waveform would be suitable? I mean, yeah, please.
Yes. So in Indian context means that what I feel is that first thing in India, it is that it is a highly dense, means it has huge population. Okay. So first thing we need to take into account is that we need to support more number of users we have to support. And second thing is that the cost should be less. How much phone bill we are paying in Europe? If that it is put on the head of our people, nobody is interested to go for that. So the cost they have to take into account. And given for a lot of people, we need to support. So what is the energy we can utilize for the cellular? Whether it can be cellular or applications, whether it is any other, whether it is broadcast, space, satellite, how much energy the country, the government is supposed to allocate for them. That also has to be taken into the account. Okay, so one reason why Cdma failed in India is that, so even though I have like orthogonality in terms of the time and frequency, so just I distinguish different users in terms of code, mathematically Cdma can support an infinite number of users. But the problem is that time they have not taken into account this thing called multi-user interference. So because of this, when I go for matched filters, or when I want, so what they will do, simply they will increase the SNR. But when multiple users are coming into the picture, apart from the channel noise, I have to take into the interference also. So what is information for me? It can be interference for the user sitting next to me. So this also had to be taken into the consideration. So I say that those people who wanted to propose some waveforms in India, in Indian context, they have to take these criteria into the picture, because already the smart city thing, they are coming up now. So a lot of missions will be involved. So when this massive deployment is happening, how much network energy efficiency I can have, how many users I can support, uh, all these things I have to take into account. Rather, for me, I say that more than speed, reliability means the reliability of the communication, number of users or the number of things I am supporting, and how much energy I'm using efficiently, that we need to concentrate upon. Because this information and communication technology in the industry means you can count all your laptops, phones, TV base stations, your mobile towers, everything. Okay, its contribution, its energy consumption way back in 2012, during that time it is around 10%. And we know that how each and every citizen in this country nowadays having a mobile phone. Some people, they are having two, three phones with them. Okay, if they buy some cheap mobile phone, if the power amplifier is not designed well, then there will be a lot of heat emissions will be there. So the contribution to the global warming is a very serious threat. So we have to keep these green communications also into the mind. So I say that at any point of time, we can sacrifice on the data rates, but when it comes to the efficient utilization of the energy, in terms of the global warming, in terms of the number of users we can support, this we should keep it in mind. Because there is no free lunch. If I want something good, there is always something bad, whether you know it or not. This is the real world.
Wonderful, so wonderful. On that note, we will now wind up this session. On behalf of the participants, Atal Academy and Goa College of Engineering, I thank you, sir, for giving us such a wonderful lecture and in such a holistic manner, sir. You covered right from the fundamentals. You took us through a journey which was, fascinating. So I thank you, sir, for first
Thank
of all.
you very, very much. Thank you very, very much. And I thank Prabhu Chandra also for giving me this wonderful opportunity.
That's right, sir. That's right. I must mention here that our industry partner played a key role in this particular presentation being possible. So thank you so much, sir. And I hope the participants have enjoyed it, and they will communicate with you, sir, maybe through email, etc. If they have any further queries. Yeah.
Yes. Okay. So I will be. Yes. So I am stopping to share. Okay.
Yes. Yeah, that's fine, sir. Yeah,
okay,
I think you have a lecture now at 11:30. That is what you told me. So you need a well-deserved break, sir. So you can please proceed.
Yes. But just I want to make this that during the December, I think on 11th, I have one more lecture which is on energy efficient techniques.